Welcome to the lecture on linear programming problem module 2. In this module, we will discuss simplex method for solving an LPP and also big M method. As you know, in 1947, George Danzig developed an efficient method called simplex method for solving an LPP with many variables. Simplex method is similar to the graphical method. Graphical method considers only two variables, where simplex method can consider more than two variables. The concept of simplex method is similar to the graphical method, in which we consider the extreme points of the feasible region for the optimal solutions. In the simplex method, we look for the extreme points of multi-dimensional polyhedron for the optimal solutions. Simplex method is based on the property that if the optimal solution of an LPP exists, it lies in the basic feasible solution. Before I explain simplex method, let me explain what do we mean by canonical form of an LPP. An LPP is said to be in canonical form if it satisfies three characteristics. First one is that it should be of maximization type, and second one is that all constraints should be of less than equal to type, and of course the decision variable should be non-negative. Next, I would like to explain what do we mean by standard form of an LPP. An LPP is said to be in standard form if all constraints are expressed in the form of equations except the non-negativity restrictions, and the right hand side of each constraint equation is non-negative. Now, we will discuss two variables called slack variables and surplus variables, which are very much needed for converting a given problem into standard form. Let me define first the slack variable. A variable which is added to the left hand side of a less than equal to type constraint to convert the constraint into an equality is called slack variable. Surplus variable, a variable which is subtracted from the left hand side of a greater than equal to type constraint to convert the constraint into an equality is called surplus variable. Now, I will come to basic solution and basic feasible solutions. We will show you how can we find basic solutions and basic feasible solutions. For this, let us consider a set of m linear simultaneous equations in n variables, where n is greater than m. This system equation can be written in matrix form as Ax equal to B, where A is an m by n matrix of rank m. If any m by n non-singular matrix B is chosen from A, and if all the n minus m variables not associated with the chosen matrix B are set equal to 0, then the solution B inverse B to the resulting system equation is called a basic solutions. The possible number of basic solutions in a system of m equations in n unknowns, where n is greater than m, is NCM, that is factorial n divided by factorial m into factorial n minus m. Basic feasible solution. A basic feasible solution is a solution which is basic as well as feasible. So, when a basic solution satisfies all the non-negativity restrictions is called a basic feasible solution. Let us take an example to find the basic feasible solution of a system of equation. We consider the system equations as 2x1 plus 3x2 minus x3 plus 4x4 equal to 8 and x1 minus 2x2 plus 6x3 minus 7x4 equal to minus 3, where the variables x1, x2, x3, x4 are non-negative. This set of equations can be written in matrix form as a1 x1 plus a2 x2 plus a3 x3 plus a4 x4 equal to b, where the column vectors a1 equal to 2 1, a2 equal to 3 minus 2, a3 equal to minus 1 6, a4 equal to 4 minus 7 and b equal to 8 minus 3. The maximum number of basic solutions that can be obtained is 4C2 equal to 6. We write the 6 sets of 2 vectors as capital B1 equal to A1 A2, capital B2 equal to A1 A3, capital B3 equal to A1 A4, capital B4 equal to A2 A3, capital B5 equal to A2 A4 and capital B6 equal to A3 A4. We also find determinants of Bi's and see that none of the determinants vanishes. This means that every set Bi of 2 vectors is linearly independent. Hence, the vectors of basic variables associated to each Bi are as given below. X B1 equal to B1 inverse B, which can be obtained as 1 2. X B2 similarly can be obtained X B3, X B4, X B5 and finally X B6. Therefore, the possible basic feasible solutions are x1 1 2 0 0, x2 22 by 9 0 0 7 by 9, x3 which is 0 45 by 16 7 by 16 0 and x4 0 0 44 by 17 45 by 17, which are also non-degenerate because none of the basic variables is 0. The other basic solutions are not feasible. Now, before we explain the simplex method, we would like to state a very important theorem called fundamental theorem of LPP. If an LPP admits an optimal solution, then the optimal solution will coincide with at least one basic feasible solution of the problem. The importance of the theorem is that to find the optimal solution of an LPP, we should look for the basic feasible solutions, as one of the basic feasible solution definitely will give the optimal solution if it exists. Now, we come to simplex algorithm. In step 1, we have to convert the given problem into a standard maximization form, and then in step 2, we should obtain an initial BFS, that is basic feasible solution. Then in the next step, we will calculate the net evaluations Zj minus Cj, where Zj minus Cj is equal to Cv xbj minus Cj. If Zj minus Cj is greater than equal to 0 for all j, then xb is an optimal basic feasible solution. And if at least one Zj minus Cj is less than 0, then we proceed to improve the solution in the next step. In this step, that is in step 4, if there are more than one negative Zj minus Cj, then we choose the most negative of them. If Zk minus Ck for some j equal to k is giving the most negative one, then Ak should be the entering vector. If all Aik is less than 0, then there exists an unbounded solution of the given problem. If at least one Aik is greater than 0, then the corresponding vector Ak enters the basis, and this column is called the key or pivot column. In the next step, we divide each value of xb by the corresponding but positive value of the key column and select a row which has the ratio non-negative and minimum. This row is called key or pivotal row, and it represents the variable which will leave the basic solution. The element lies in the intersection of key row and key column is called key element. In the next step, we convert the key element to unity by dividing its row by the key element itself and all other elements in this column to zeros by using the pivotal row. Next step, we will go to step 3 and repeat the procedure until all the entries in Zj minus Cj are either positive or 0, or there is an indication of an unbounded solution. Before I take up an example to demonstrate the simplex method, let me show you how a simplex table is formed. This slide shows different columns for forming the simplex table. First, Cj's are the costs components, and the components of B are the components for the recurrent vector. Aij's are the elements of the matrix A, and B denotes the basic vectors, and xb denotes the basic variables, and Cv denotes the component of the cost components for the basic variables. Now we consider an example and demonstrate the simplex method. Suppose that we have to minimize z equal to x1 minus 3x2 plus 2x3 and subject to 3 constraints, and also we have non-negative expressions for the decision variables x1, x2 and x3. First, we convert this problem in standard form. For this, we convert the objective function into maximization type and each inequality constraint into equation by introducing slack variable. Here, we introduce 3 slack variables x3, x5 and x6 to the constraints and rewrite the problem in standard form as maximize z1 equal to minimize minus z equal to minus x1 plus 3x2 minus 2x3 plus 0 into x4 plus 0 into x5 plus 0 into x6, subject to 3 equations as shown in this slide, and the variables x1, x2, x3, x4, x5 and x6 all are non-negative. Now, if I put this problem into simplex table, then we see that the vector A4, A5 and A6, they form a basis because A4, A5 and A6, they are linearly independent. So, in the basis we have A4, A5 and A6, and the corresponding variables are x4, x5 and x6, and the cost components for the basic variables are all zeros. Then we see that we calculate that Zj minus Cj, and from the values of Zj minus Cj, we see that minus 3 is the only negative quantity. Hence, the vector A2 will enter into the basis. Then we have to calculate the minimum ratio to find which vector will depart the basis. For this, we consider the components 4 and 3 of the vector A2, and we consider the ratio 12 by 4 equal to 3 and 10 by 3 equal to 3.33, so that since 3 is minimum, therefore, if the corresponding vector A5 will depart the basis. In the next iteration, A4, A2 and A6 form the basis. From the values of Zj minus Cj, we see that Z1 minus C1 is only negative, and therefore, the corresponding vector A1 will enter the basis. Since A1 has only one positive component, which is 5 by 2, the corresponding vector A4 will be the departing vector. So, in the next iteration, A1, A2 and A6 will form the basis. We then calculate the values of Zj minus Cj and find that Zj minus Cj is greater than or equal to 0 for all j. Hence, the optimality condition has been satisfied. The optimal solution can be read from the last iteration as x1 equal to 4, x2 equal to 5, x3 equal to 0. Here x3 is not in the basis. So, it is a non-basic variable, and therefore, we take x3 equal to 0. The corresponding minimum value of z is minus 11. We have some interesting observations from this discussion. Firstly, we are moving from iteration to iteration for finding the optimal solution. That is, we are testing the basic feasible solution in each iteration for the optimal solutions. Since there are finite number of basic feasible solutions, we could reach the optimal solution in a finite number of iterations. Secondly, for finding the optimal solution in simplex method, we need to start with an initial BFS, that is basic feasible solutions. Unless we get an initial basic feasible solutions, simplex method cannot be applied. So, for some problem, if we are unable to find an initial basic feasible solution by considering slack variable and surplus variable, we need to introduce some other variable called artificial variable, and the method is called big M method, which I am going to demonstrate you in the next slide. Let me define again what is an artificial variable. In the standard form of an LPP, when the decision variables together with slack and surplus variables cannot afford initial basic variables, a non-negative variable is introduced in the left hand side of each equation, which lacks the starting basic variable. This variable is called artificial variable. So, by introducing artificial variable, we will be able to get an initial basic feasible solution to start with simplex. Now, we will take an example to explain how can I solve an LPP by big-M method. We consider a minimization problem as shown in the slide. The constraints are all greater than equal to type. So, we need to introduce first the surplus variable. Even if we introduce two surplus variables x3 and x4, we are unable to get an initial BFS. Therefore, we introduce two artificial variables x5 and x6 for the two constraints, and in the objective function the coefficient of each artificial variable is taken as -m, where m is a very large positive quantity. That is why the method is called big-M method. Sometimes this method is also called penalty method. When we put this problem in simplex table, we see that A5 and A6 form the basis, and Z2 minus C2 is the most negative quantity. Therefore, A2 will be the entering vector, and from the minimum ratio A6 will be the outgoing vector. In the next iteration, Z1 minus C1 is most negative. Therefore, A1 will be the entering vector, and from the minimum ratio A5 is the outgoing vector. Here the computation for the column vector A6 is left out, because when an artificial variable leaves the basis, there is no chance that it will enter the basis again. In the final iteration, Zj minus Cj is greater than equal to 0 for all j, hence the optimality condition is satisfied. The optimal solution is x1 equal to 4, x2 equal to 1, and the corresponding minimum value of z is 11. We would like to tell you some criteria for different solutions. The current solution is an optimal basic feasible solution if no artificial variable remains in the basis and the optimality condition is satisfied. The current solution is an optimal degenerate basic feasible solution if at least one artificial variable appears in the basis at 0 level and the optimality condition is satisfied. The problem has no feasible solution if at least one artificial variable appears in the basis at the positive level, though the optimality condition is satisfied. In this module, we have learned the concept of basic solution and basic feasible solutions. We have also derived basic solution and basic feasible solutions for a system of equations. We have learned the method of simplex for an example, and where we have seen that the method fails if we are unable to start with an initial basic feasible solutions. In such a case, we have to introduce some artificial variable, and then only we can get an initial basic feasible solution to start with the simplex, and that method is called the big-M method, which we have also learned how to handle. With this, we end this module.